Yes, so let's start. Yes, so good morning, everybody. So let me quickly summarize what we did in this course so far. In this course, we had chapter 2, 3, 4. These three chapters are actually related to physical layer, the first layer, what happens in the first layer. And then chapter 5 and 6 are related to the second layer, okay? So in chapter 5, I explained error and the flow control and also framing, because this is two things are done in the second layer. And also one of the most important things that are done in the second layer is actually medium access control. And under medium access control, first of all, I explained random access. Under random access, I explained Aloha, slotted Aloha, and then I explained CSMA, and then CSMA with collision detection, and CSMA with collision avoidance. And then after that, I explained controlled access, which is either when we have a master and a slave this way, and this protocol, we call it pooling. The other one here is actually token passing, as I explained last time, okay? As I said before, you should understand always in case of random access, always we have collision. Always there is a chance to have collision, but we try to minimize this chance, okay? And all these algorithms are distributed, okay? Here in controlled access and also channelization, it's impossible to have a collision, okay? So there is no collision at all, because the way we do these two protocols. So here we have central unit, and in the second one here, in token passing, it's distributed. There is no central unit. Last time I started to explain the idea of channelization. I started with, we have three ideas here: time division, multiple access, here time division, multiple access, and also frequency division. So the idea of time division is, as I said last time, okay, so if the bit rate of the cable is actually R, so what we are gonna do is we're gonna split the time, okay? So here, as you see here, this is one time slot. So one computer can use the full bit rate of the cable during this time slot, okay? Next time slot is gonna be for computer 2, computer 3, computer 4. That means, for example, if you look at computer 1 transmit here during this time slot, and then it's gonna stop, and then here do it again here, and so on. You got what I'm saying? So during the time slots, maybe there is something confusing here a little bit. So you should know, yeah, that if the bit rate of the cable is R, so actually the bit rate every computer is going to receive is going to be R divided by N. This is the average, right? Because N is the number of computers we have. Because actually I'm gonna split, or I'm gonna divide this R by N computers. Okay. So if you see the average, you will see I transmit here, and then I'm gonna transmit here. So if you see the average is gonna be R divided by N. Every computer is gonna receive R divided by N. You should ask, that's why you call it like a channelization. The word channelization means you have your own time slot. This is the meaning of it. When I come to frequency, I'm going to tell you, you have your own frequency band. That's yours. Okay. If you don't use it, no one else will use it. Okay. As you see here, computer 2 does not transmit. So, and for sure, this is a bad thing, because you are using, you are wasting, or you are not using the resources you have, because here computer 2 does not have anything to transmit. So this time slot is gonna go idle. For sure, we need synchronization here. All the computers should be synchronized. Yeah. So here, the most important thing you should understand here: number one, you don't continuously transmit. You only transmit during some time slots, and when you transmit, you actually take the full bandwidth, the whole bandwidth you take it. Okay. you need to compare between this slide and the other slide here. Yeah, this one, okay, for frequency. So in frequency, you see for the time you always transmit, all the time you transmit. But I'm gonna divide, or I'm gonna split the frequency. I'm gonna divide the frequency between the different computers. So here I'm gonna give you a smaller frequency, but you are gonna transmit all the time. If you look at the bit rate, it's still the same thing. It's N divided by R divided by N. The bit rate is still the same thing, R divided by N. Okay. But the difference here, you transmit all the time. The other one, you transmit and then you wait to transmit again. But anyway, but still, if you look at the average bit rate, you will find it's the same, R divided by N. So as I told you, here's the idea. We divide the spectrum into bands, okay? And every computer can transmit in one band, okay? And because and that's why here we have multiple transmissions. We have multiple transmissions at the same time. But here here we have only one transmission by one computer, okay? Here we have multiple transmission and we don't have collision, as I told you before, simply because every computer is going to transmit in a different frequency band, okay? That's why we don't have collision. Again, we still have the same problem. If every computer has its own band, if you don't use this frequency band, no one else will use it, so it's going to be wasted, okay? So last one here, we call it CDMA. C is actually for code, F for frequency, T for time. This one, T, because we divide the time, we split the time. Here we divide the frequency. Here we have codes, different codes, as I explained last time. Okay, so if you see what we are going to do here. So here, every computer has a code, okay? And using this code, you can transmit. If you don't have a code, you cannot transmit, okay? So every computer should have a code, and you have to use this code. What do you mean by code? Just as I started to explain last time, it's just a vector. This vector has some numbers. That's it, some numbers. That's the meaning of a code, okay? So I'm going to elaborate today, but the main idea here, just to make a comparison, if I compare this one with the frequency with FDMA, in FDMA we have continuous transmission. It's the same thing here also. We always you transmit. Okay, so this is different from this one. Okay, so CDMA differ from FDMA because only one channel occupies the entire bandwidth. It differs from this one because we have different computers. All the computer, no time sharing here. So all the computer can transmit at the same time, as you will see right now. So let's start with the idea of code. Okay, this was the basic idea I explained last time. So the basic idea, as I told you, every computer has a code. For example, this one has C1, C2, C4, and C3. This is the code. You don't change the code, so you're going to continue using the code for different data. What you are going to do here, when I receive data, like when I have data, I want to transmit data, you are going to multiply this data by your code, and then you put it on the channel. This computer will do the same thing. I'm going to get data, multiply by a code, and then put it on the channel. Same thing and same thing, okay? Because this computer is going to put this signal on the channel. At the same time, the result will be addition of these channels. I told you before, if you have here one computer is going to put in here 5 volt, another one putting 7 volts, so you will see it is 12 volt. Okay, so that's exactly what's happening here. So every computer, so this is the data on the channel, or the signal on the channel. For sure, this is like the main idea. I'm gonna give you details right now. So here, this is the signal of the channel. So now the question is that so what if I want to receive D1? So if you have a computer that I want to receive D1, or I want to receive D2, I want to receive D3, okay? So I told you last time, the idea here is this code, I'm not going to select these codes randomly. They are not random, okay? I'm going to select this code so that if you have one code like CI multiplied by CI, I can be any number, for example, in this case, 1 to 4, okay? If I multiply a code by itself, I'm going to get number 4. Which is number n. N here, or 4, is actually how many computers we have, okay? So also, when I multiply CI by CJ, and the I, I does not equal J. So if I multiply any code by any other code, different code, I'm gonna get 0. So you have to understand these two, okay? So I'm gonna select the code so that when I multiply a code by itself, I'm gonna get n number, the number of computers. But when I multiply a code by any different code, I'm gonna get 0. So why you need these two? To be able to receive the data here. Okay, so the idea is very simple. If I want to receive the data of computer 1, so I'm gonna multiply the data, because that's what I'm gonna receive. That's what this is the physical signal you are gonna receive. I'm gonna receive this physical signal. So given this physical signal, how you can extract D1 if you want to get D1, or D2 or D3 or D4, okay, from this signal. This is a signal. Okay, this is what you are gonna receive as a signal. Okay, so as I told you, all what I'm gonna do, if I wanna get D1, very simple, I'm gonna multiply this one by C1. If I wanna get D2, so I'm gonna multiply this one by C2, and so on. But why? What is the reason? Simply, the reason is, if you see here, if I multiply this one by C1, okay, so C1 times C1 is take a seat. C1 times C1 is 4. C1 times C2 is 0. C1 times C3 is 0. And this one here is 0. Okay. So by this way, I'm going to get 4G1. You can divide by 4 and then you can get G1. Okay. I give you an example of C1. You can repeat it for C2, for C3, then it's the same thing. So all what you have to do after you receive the signal, you have to multiply this signal by the code of the data you wanna receive or you wanna retrieve from the signal. Okay. Any questions? Last time, this is the basic idea. So last time I started to give you details. Okay. How this code looks like. Okay. How when you multiply a code by itself, you are gonna get 0. Sorry, you are gonna get n. If you multiply a code by another code, you are gonna get 0. How we can do that? Okay. So actually, this code is actually a vector. Okay. So that means every code is actually a vector. Okay. How many elements we have in this vector? The number of elements actually is equal to n. The number of computers we have. Okay. So if I have 4 computers, so I should have 4 elements. If I have 10 computers, should have 10 elements, and so on. Okay. So we have numbers here. For example, A, B, C, D. For example, some numbers. Okay. But here I put it in general A, B, C, D. Okay. So now there are 2 operations you should understand for vectors. Okay. The first operation is, if I have a vector, and if I want to multiply vector by vector, this is what we call inner product, as I told you last time. Let's have some example. For example, here I have 1, 2, 3, 4, and then I have another vector. I'm going to say, for example, 2 in any numbers, 1, okay, 0, 3, any numbers. Okay, so so the first thing here, how can you multiply 2 vectors together? That's what we call inner product. The way we do it, actually, you are gonna multiply the first element by the first element here. Okay, so 2 times 1 is actually 2, plus you are gonna multiply the second element by the second element here. Okay, 2 times 1 is actually 2, so plus 2. You are to multiply the third element by the third element, which is 0, so plus 0. And then you are going to multiply the third elements by the third elements here. So it's going to be plus 12. That's it. And then you add everything together. So if I multiply, very easy idea. So when you multiply vector by a vector, you are going to get a number, not vector, a number. Okay. So this is the first operation we need. The second operation we need is actually when you multiply a vector by a scalar. A scalar here is a number. For example, I want to multiply 3 times. So 2 operations we need. Number 1, how to multiply vector by vector. That's what we call inner product. Or how can you multiply number by a vector? Okay. For example, here you have 2, 1, 0, any numbers. Okay. For example, 3, something like that. When I multiply a constant number by a vector, that's what we call you multiply scalar by a vector. And how can we do this operation? You actually multiply this one by each element. Okay. So it's going to be like 3 times 2 is 6. 3 times 1 is 3. 3 times 0 is 0. 3 times 3 is 9. That's it. Any questions? That's what we need right now. Now I'm going to give you more details. Okay. For example, as I told you here, so here we have here, we assume we have 4 computers. Okay, 4 computers. Every computer has a code. And how many elements we have here in every code, how many elements should equal to the number of computers. If you have 4 computers, so it should be 4 elements here, as you see. Okay. And then forget for now, forget, I'm going to explain also later or just today in details how we can come up with this special code. They are special code because they have to achieve what I told you before. Any CI times CI, you will get 4 or N. In general, N, right? Here, N is 4 computers or 4 elements. Okay. Also, CI times CJ, where I does not equal J, should equal 0. So multiply any code by any other code, you are going to get 0. So they have to achieve these 2, right? So the way, for example, we have these 4 codes. Forget how I calculated them. At the end of this lecture, I'm going to tell you an approach that you can use to calculate this code to achieve these 2 properties. Okay? So let's start. But at least I want to make sure these codes. I want to tell you. I want to tell you that these codes can achieve these 2 requirements. So as you see here, okay. For example, if I multiply any code by itself, I'm going to get 4. Here I tried C1. I multiplied by C1. I multiplied C1 by itself. So 1 times 1 plus 1 times 1 plus 1 times 1 plus 1 times 1. Okay. So I got 4. If I multiply C4, for example, by itself, also I'm going to get 4. For example, 1 times 1, this one here. Okay. And then -1 times -1, which is here, plus -1 times -1, which is here. 1 times 1. So in total here, I got 4. Okay. So you can try, when you go home, you can try C2 and C3. Okay. Now let's try to, if I multiply any code by any other code, I told you have to get 0. For example, here I tried 2 and 3, I tried 1 and 4. So let's see, for example, if I try here 2 and 3, okay? So here I'm going to multiply the first element by the first element, which is here, okay? And then the second element by the second element. Anyway, if you add everything, you are going to get 0. Same thing if you multiply C1 by C4. Any questions? Okay, now I'm going to give you more details, okay? Everything in details now. So here, So here I'm going to tell you how we're going to use the code, how we're going to convert these binary numbers, and this code converts them to voltage, to signal. Okay. So here, for example, as just an example, we're going to here, if I want to send 0, so 0 is going to be equivalent to -1 voltage. 1 is equivalent to +1 voltage. Silence means I'm not going to transmit. So it's equivalent to 0. So we have 3 cases here. Either the computer want to transmit bit 0, or the computer want to transmit bit 1, or the computer is not transmitting anything. Okay. So if you're transmitting 0, so this will be represented by -1 voltage. This one is represented by +1 voltage. This one is represented by 0 voltage. Okay. So, and then here in this example, very simple example, for example, here, I'm going to show you how can we use the code to transmit the signal and how the signal looks like. Why keep saying signal, signal, signal? Is this signal sine wave or digital signal? That's what you are going to see right now. And how we're going to do it. That's what I'm going to explain. So if you see here, first of all, this computer want to transmit 0, bit 0. So here is going to be -1. Okay, 0, -1. Silence, I'm not going to transmit anything, which is 0, as 0 volt, as I told you. Bit 1, which is +1, okay, for bit 1. Now, all what I'm going to do here, I'm going to multiply, first of all, because we have here 4, we have 4 here, we have 4, the code has 4 elements. We're going to transmit every element in 1 time slot, so it's going to take 4 time slots. I'm going to clarify it now, okay? But it's going to be more clear. But at least now, what I'm going to do is I'm going to multiply the data I'm going to transmit here, which is -1. I'm going to multiply it by the code I have. When you multiply it by the code, so -1 times this one here, as I told you. So I'm going to multiply -1 by the first element, which is -1 by the second element, and so on. So this is the data. This is the data I'm going to transmit. That means in the first time slot, I'm going to put -1 voltage. In the second time slot, I'm going to put -1 voltage. So this signal, if you look how this signal looks like, this signal looks like here in every time slot. You are going to put -1, -1, -1, -1. Okay, so that's what should be done in this computer. Let's look at this computer here. This one is going to transmit bit 0, okay, which is actually -1. Here you transmit -1. So multiply actually -1 by each one here. It's the same idea. You multiply -1 by each element here, and this is what you are going to put. So here in the first time slot, you are going to put -1. Here, because you multiply 0, you're going to put 0, and here you are going to put +1. So if you see what is the result, here in the first time slot, here, this one is going to put -1, this one is going to put -1, this one is going to put +1. So that's why the result is -1. Okay. If you look at the second time slot, this one here is going to put -1, as you see here. This one is going to put +1, and this one is going to put -1. So that's why the result here is -1. Okay, and it's the same thing for the other ones. For example, here this one is -1, -1, -1. So it should be here -3. So this is the vector we are gonna get here. Okay, so you can see it as like a signal. That's exactly what I told you. As a signal, this is what you are gonna transmit: -1, -1, -1. As you see here, this one is actually -1, +1, -1, +1. This way, as you see it. This one is 0, 0, 0. Okay, this one is actually +1. And then in this time slot, -1, and this is the signal on the channel, which is actually the summation, because this -1, -1, and then +1, -1, and then this one is -1, +1, -1 is, and so on. It's just summation. Okay, so this is the data we're gonna get on the channel. So as I told you before, if I have this data with the channel, how can I extract? How I can extract the bit 0? Or because this is the data you transmitted, or here bit 0, or actually bit 1 here, or 0 here. Okay, as I told you before, all what you have to do, I have to multiply this data by the code. So if I multiply this data by C1, I'm gonna get bit 0. If I multiply by C2, I'm gonna get bit 0 here, I get bit 1, and so on. Okay, so and this is the example I'm giving you here, the example. So here I'm gonna multiply this signal. Okay, this is here. This is the data. So this signal is actually this data here. I'm going to multiply this data by the code of computer number 3. For example, just an example. I actually tried every one of them here. So if I multiply this data by computer number 3, at the result, I'm going to get -4. And then you have to divide it by 4. Always you have to divide by 4. After you do that, I'm going to get here -1. And as I told you before, -1 is actually 0 bit. So now I'm going to do the opposite. So what I did in the very beginning, if I want to transmit, let me go back here. Yeah, if I want to transmit bit 0, so I'm going to convert it to -1. Now I'm -1 voltage. So now I'm going to do the opposite. If I have -1 volt, so I'm going to convert it to 0. So that's what I did here. So after I did the calculation, I got -1 voltage. So this means it is 0. That's true because we transmitted 0. So I tried it, just to understand it more, I tried it with another computer. So this is computer, I think this is computer number 1 or 3, which is have the code +1, +1, +1. Which computer is it? Yeah, sorry, this one, yeah. So here I'm gonna try with computer 1, it has to be bit 0 as well, because that's what bit 0 said. So if I do it, the same thing, I got bit 0, I got -1 voltage, which is bit 0. But if I try it with computer number 4, so actually I got 4, which divided by 4, so it's going to be +1, and +1 is actually bit 1. When I try it with computer 3, no data, I got 0. 0 means no data. You got what I'm saying? Any questions? So now it's similar to what we did before, number 1. So here in four time slots, I'm gonna transmit four bits in 4 time slots. Okay, so that means every computer is gonna take R divided by N as well. So similar to what we had before, the bit rate, because every computer in 4 time slot you're gonna transmit only one bit. Okay, So it's similar to what we had before. The bit rate for every computer is going to be R divided by, similar to the other one. Also similar to the other one. If you don't transmit, no one else will transmit. So you are going to lose. We are going to lose this one. So for example, here, this computer here, this computer does not transmit here. Okay. So that, and no one else can use it. Okay. Because this is your code. So we are going to lose this transmission capability. The last thing here I'm going to teach is actually, I'm done with CDMA, but what I'm going to teach a very simple approach. How can we come up with the codes? You are telling me we should have codes, and these codes have to achieve two main requirements. Number one, CI times CI is 4 or N, whatever N is number of CI times CG is actually 0. How can we make sure we can achieve this? Okay, so actually we're gonna do very simple approach. This approach is called Walsh tables. So this is the name of the table. It's called Walsh table. Let's see how it works. Okay, this is the basic rule. Number one, assume we have only one computer. Okay, for in this case, I'm gonna call it W1. Okay, so in W1 here I'm gonna start with positive 1, or you can start with negative 1. So here we have only one computer. Okay, given this table or this code, this is like a code. Assume this is a code for one computer. Okay, if we have a code for one computer, it's easy to calculate the double of number of computers. Okay, so if you have W of n, in order to get W2n, so if I have Wn, if I have the table for Wn, okay, n is the number of computers. For example, if I have W2 means I have 2 computers. That means the vector has two numbers. Okay, so I can get W4. So this approach, as you see right now, you can calculate W1, and then from W1, as you see, so let's look at this one here. So W1 here, we assume we have one computer. Okay, from W1 I can calculate W2 here if we have two computers. Okay, and from W2 I can calculate W4. So always you can calculate the double. Okay, 4 you can calculate 8. Okay, and then you can see here in this matrix, actually this is the code and this is another code. So every row is a code. This is the code, and this is a code, and this is a code, and this is a code. So let's see how it is calculated. Very easy, very trivial. So as you see here, if you have one W, you are gonna just you are gonna copy them here, and here you are gonna put the negative of this one. So you multiply all the elements by negative. So can you clarify? I'm gonna clarify. Look here. For example, this is W1. How can I calculate W2? Okay, from W1. All what you have to do, just repeat, as we see here. I'm gonna repeat it, and then what I'm gonna put here is the negative of this one. This one is positive 1. I'm gonna put negative 1. Okay, I'm gonna repeat again. If I give you, for example, this can be a question in exam. I can give you W2, for example, and I ask you to calculate W4. How can you do that? Very easy, very trivial. All what you have to do, you have to repeat W2. That's it. And then what we have put here is actually negative of W2. And negative of W2 means every element, you multiply every element by negative 1. Very easy, right? And again, if you have W1, you can calculate W2. If you have W2, you can calculate W4. You have W4, you can calculate W8, and so on. Okay, just always by 2. Okay. I have here a very simple example. Here I'm giving you, and again, once you make this matrix, once you have this matrix, actually every row here is going to be one code, and you can try when you go home. You can try. If you multiply code by itself, you are going to get 0 or not. So you are going to get 4 or not. If you multiply code by another code, you can see if you are going to get 0 or not. Okay. So you should understand here. One important thing you should understand, if we use this approach, always you can calculate for 1, for 2, for 8, for 4, every time multiplied by 2. So that means the number of computers here always has to be 2 to the power of m, always 2 to the power of something, because every time you multiply by 2. Okay. So, okay, what happens, and this is, I think, one example here. What happens if I tell you I have 90 stations, I have 90 computers, okay? 90 computers. That means, so ideally, every vector should have 90 numbers in every vector, okay? But actually, as I told you, this number has 2 to the power of something. We don't have 2 to the power of something give you 90. We don't have this one. The closest one is actually 2 to the power 7, which is 128. You got what I'm saying? So it has to be 2 to the power 6, and then after that 2 to the power 7. That means I can't have a vector for 90. The closest one is actually 128. So now I'm gonna make a vector for 128, not for 90. That okay? Here, this is just a simple example. It's just coming from here. So if I tell you what are the codes here, if for example, if you have 4 computers, what are the codes? This is one code. Every row is one code. Okay. Again, the other thing I want to teach here to start as a quiz is, for example, I'm gonna keep saying it again. For example, here, if I give you W4, can you calculate W8? Yeah, very trivial. You just follow this one. I'm gonna repeat W4 here completely. I'm gonna repeat W4 here. I'm gonna repeat W4 here, and then here is gonna be the negative. So here I'm gonna flip all the signs here, just to multiply everything by negative and just to put it here. By this way, I'm gonna have 8 by 8, right? Matrix 8 by 8. Okay. Any questions? I think that's enough for this chapter. I'm gonna start in next lecture. I'm gonna start chapter 7. So chapter 7, we finished layer number 2. Now we're gonna go up to layer number 3. So everything I'm gonna explain is gonna be related to layer number 3. Yeah. Oh, sorry.